Now in this lecture I will discuss about the effect of concentration of the reacting species in a Daniell cell on its EMF. In the previous lecture I have discussed how we get the EMF of Daniell cell, and using Nernst equation we obtained that E cell equals to E0 cell minus 0.0591 by 2 log product by reactant, that is Zn2 plus third bracket by Cu2 plus third bracket. Now this is at 25 degrees centigrade, since we have put the value of temperature here. So this is the Nernst equation for the cell reaction that is occurring in the Daniell cell. Now case 1 that we have discussed before is that we have taken concentration of Zn2 plus equal to 1.0 molar, and we have taken concentration of Cu2 plus to be the same as that of zinc 2 plus, it was also 1.0 molar. Now if we put the value, we will get this one we have obtained in the previous lecture. It was 1.1 volt and it is 0.0591 by 2 log 1 by 1. We put the values in this equation. So it is log 1 is 0, so this whole term vanishes and we have E cell equals to 1.1 volt. Now if we start with this concentration and if we wish to measure the EMF, after elapse of certain time there will be change in concentration of Zn2 plus in the anode chamber and Cu2 plus in the cathode chamber. So what will happen after elapse of certain time? Say it is at t equal to 0 when we start drawing current from the Daniell cell, and say after elapse of certain time, case 2, what will happen? Now obviously concentration of Zn2 plus will increase and concentration of Cu2 plus will decrease. For this you have to feel the phenomena that is occurring in the Daniell cell. So we have Zn electrode dipped in ZnSO4 solution and copper electrode dipped in copper sulfate solution, and we connect it externally. Now as reaction proceeds, Zn is getting converted to Zn2 plus. As we draw current from this circuit, Zn atoms leave the electrode in the form of Zn2 plus ion and it pass into the solution. So as time elapses, as reaction proceeds, concentration of Zn2 plus increases in this chamber, and this electron goes through the external circuit and it is getting absorbed by copper 2 plus and it deposits on this electrode. So concentration of copper 2 plus will decrease in the cathode chamber as reaction proceeds. So copper 2 plus will decrease and Zn2 plus will increase. Now for example, say this to be 1.5 molar and this to be 0.5 molar. See, copper 2 plus is decreasing here since copper 2 plus is getting deposited here in the copper electrode, and zinc atoms are getting into the solution in the form of Zn2 plus ion. So Zn2 plus will increase. Now if we put this value, we will get, here it is E0 cell. This will not depend on the concentration, and it will be 1.5 by 0.5. So we need calculator for this purpose. So it is log 1.5 divided by 0.5 equal to 0.477 into 0.0591 divided by 2. So it is 0.014. Now, so the value will be 1.0859 volt. So see, as the reaction proceeds, the voltage is decreasing. That should be, since at the start it has voltage 1.1 volt, and the chemical energy is responsible for this voltage. Now as the reaction will continue to happen, it will move towards equilibrium gradually. So there will be decrease in the chemical energy. So voltage must fall, and at equilibrium it will come to 0. So this is in accord with the physical interpretation. So the voltage must fall. So it is falling. See, this was 1.1 volt at the start, and after a certain time it is getting 1.08, and as it will proceed, it will gradually fall and will come to 0. When it will come to 0, the voltage, when the voltage EMF will come to 0, the battery will come to an end. Now another thing, if you change this concentration intentionally, not just in the course of reaction process, just if you want to have case 2, you just put 1.5 molar ZnSO4 solution instead of 1.0 molar, and 0.5 molar CuSO4 solution instead of 1.0 molar. Then also you will get a lower voltage. So if it is your starting concentration 1.5 molar for Zn2 plus and 0.5 molar for copper 2 plus, it will be this 1.0859, it will be your starting voltage. Since you see Zn2 plus is greater than this one, Zn2 concentration of Zn2 plus is greater than the previous case. So it will prohibit Zn2 plus ion from further coming into the solution owing to repulsion. And see, copper 2 plus is less in this solution. So osmotic pressure will decrease, and there will be lesser probability of deposition at this electrode. Now oxidation of zinc at the anode favors the current production, and tendency of zinc to oxidize into Zn2 plus contributes to the EMF of the cell. Also, tendency of deposition of copper 2 plus in the form of copper in this electrode contributes to the EMF of the cell. Now since you are increasing the concentration of Zn2 plus, it will prohibit Zn2 plus from further coming into the solution owing to repulsion. So oxidation part will be prohibited. So that is going to decrease this electrode potential. And again, owing to the decrease in Cu2 plus ion, that is from 1.0 molar to 0.5 molar, the osmotic pressure of copper 2 plus decreases, and it will it will show a lesser tendency to get deposited at the copper electrode. So the reduction part is also affected. Both the oxidation and the reduction part is affected. So that is going to decrease the cell EMF, and that is the result. We get this. We get the voltage 1.0859 volt instead of 1.1 volt. So voltage will decreasing. Now if we take case 3, if we make it 0.5, if we make it intentionally 0.5 and this one as 1.5, so I am reversing the situation. That is, we take Zn2 plus concentration greater than case 1, less than case 1, and copper 2 plus concentration of copper 2 plus ion greater than case 1. So this is 0.5 molar from 1.0 molar and 1.5 molar from 1.0 molar. So let us predict first that what is going to happen. We are decreasing the concentration of Zn2 plus ion. So if concentration of Zn2 plus ion decreases here, there will be a greater electrolytic solution tension compared to the osmotic pressure. So more and more Zn2 plus will pass into the solution, since concentration of Zn2 plus is less here. So oxidation part will be activated. And see, copper 2 plus ion has a greater concentration compared to case 1. So the osmotic pressure will rise here, since copper 2 plus concentration is much greater. So there will be greater tendency of deposition of copper 2 plus in this copper electrode. So reduction part will be more activated. So compared to this case, in case 3 we will get both the oxidation and the reduction part to get activated. So it must give a higher voltage. So let us see. Now the Nernst equation has a definite format. Just you have to put the values. So product Zn2 plus is the product. So you put here 0.5 and it is the reactant. So we put here 1.5. Now see what will happen. We use again calculator. So it is log 0.5 divided by 1.5 into 0.0591 divided by 2. Now see, we get a negative term here. We get negative here just for this calculation, since within the parenthesis of this logarithm we have fraction less than 1, we must get a negative sign. Now this negative and this negative will add to this voltage. So we get 1.114. So we will get voltage 1.114 voltage. So as we have predicted that voltage is going to increase if we have a choice of this compared to this case, then voltage must increase, and that is the result. So the EMF of the cell increases. The EMF of the cell increases when concentration in the anode chamber decreases and concentration in the cathode chamber increases. So in this way, if you tune the concentration of the reacting species, then you can control the EMF of the Daniell cell. Now another important thing, so I will discuss this again when I will show you how a concentration cell work. So I have shown you this relation, how it come into picture. So del G equal to del G0 plus RT ln Q. This is for the standard state. Now when equilibrium is achieved, when equilibrium is achieved, we will have del G equals to 0. Now this is the driving force. If del G equals to negative, the process will run spontaneously. If del G is positive, the process will not run. It will be a non-spontaneous process. Now if its value is 0, then it will guarantee that the rate of forward reaction will be equal to the rate of backward reaction, or there will be no net reaction. So del G equals to 0 means equilibrium process. That equilibrium is achieved, and there is no increase in the disorderness any further and no decrease in the orderness of the system. Now at del G equal to 0, we have Q equals to K. Since you can remember, I have told you that Q is product concentration by reactant concentration. Now as the reaction continues, there is a gradual change in the values of these two concentrations. Zn2 plus changes from an initial value, Cu2 plus concentration of Cu2 plus changes from an initial value, and this change continues to happen from the start until equilibrium is reached. And when equilibrium is reached, it will attain a definite concentration. That is the equilibrium concentration of Zn2 plus and equilibrium concentration of copper 2 plus. Then this Q is said to be K equilibrium, that is the equilibrium constant. So when del G equal to 0, equilibrium is achieved and Q is replaced by K. So if we put here, we will get 0 here, and we will get del G 0 here, and this will be RT ln K equilibrium, or RT ln K equilibrium equals to minus del G 0. Now you can remember, I have shown you that del G equals to minus NF E cell in previous lecture, and del G naught in standard state we have minus NF E naught cell. That is, the standard Gibbs free energy change is related to the standard EMF of the cell. Now we put this value minus NF, del G equals to minus NF, so it will be minus minus, it will be plus NF E0 cell. Now if we now for ln Q, ln K equilibrium, it will be NF E0 cell by RT. Now when we take log, this is log natural, 2.303 will come out, and we take it to the right hand side. Equilibrium is, I am not writing any further. This K means equilibrium constant. So it will be NF E0 cell by 2.303 RT. Or log K equals to N E0 cell into I can rearrange this expression in the form of this expression. So it is N E0 cell here, and 2.303 RT upon F, I am taking it in this form. Now we know at 25 degrees centigrade this has a value of 0.0591, and for Daniell cell N will be 2. So it will be 2 into, now this value is 1.1 volt, and this will have a value of 0.0591, but so volt let us remove the unit. So it will be 2 into 1.1, 2 into 1.1, and this value is 0.05991, and it is in the denominator. So it will give us divided by 0.0591 equals to 37.22. So we are getting the value 37.22. Or K equals to 10 to the power, since log K equals to this one, we have K equals to 10 to the power 37.22. Now 10 to the power 37.22 is 1.678 into 10 to the power 37. Now what does this mean? We have determined the value of equilibrium constant for the Daniell cell. So when this Daniell cell will not be able to produce any current, that is it will be dead, it will come to an end, then it is said to have achieved equilibrium. Now at equilibrium the value of K is this one. Now the reaction occurring in the Daniell cell is Zn plus Cu2 plus arrow Zn2 plus Cu. So this is product by reactant. So this is Zn2 plus equilibrium by Cu2 plus equilibrium. Now the activity of this copper and zinc is 1. You all know this. So we have Zn2 plus equilibrium equal to 1.678 into 10 to the power 37 into Cu2 plus equilibrium. Now what this implies? You see, at the end of the reaction in the Daniell cell, the equilibrium concentration of Zn2 plus that is obtained is 10 to the power 37 times greater than that of copper 2 plus. So the product that is obtained is 10 to the power 37 times greater than that of reactant. So it is very, very less. Minor amount is left at the end. The concentration of the product is 10 to the power 37 times greater than that of copper 2 plus. So this is left in negligible amount, and we can say that almost all the reactant has been converted into product. So Daniell cell is commercially promising. So if you are a customer of Daniell cell, you will be satisfied, since there will be no loss. So that's all.